Now, topic of discussion related to beta carotene, right? So first of all, if we talk about beta carotene, so as our earlier discussion, it occur in all the green plants, right? It occur in all the green plants. It is isolated, right? It is isolated from carrots, right? So जो गाजर होता है उससे इसे isolate किया जाता है, right? And it is exist in all green plants, right? जो भी green plants होते हैं उन सब में ये exist करते हैं, right? So it is important point. Now the point come, what about structure of beta carotene? So we had a discussion on the structure of beta carotene, right? So you can see in beta carotene, this is cyclohexene, two cyclohexene ring, where 1, 2, and 3 methyl group here, and 1, 2, and 3 methyl group here, right? And rest acyclic part. You can see here rest acyclic part where isoprene units, right? Connected isoprene unit, right? 1, 2, 3, 4, 5, and here methyl group, here 1, 2, 3, 4, 5, here methyl group. So in this way, right? In beta carotene, you can say it is terpenoid because of it follow isoprene rule, right? And second important thing, there are cyclohexene, two cyclohexene molecule. Now, how do we clear structure of carotene, right? Now, what about their molecular formula? Molecular formula clear by analytical data, right? It is C40H56, 40 carbons and 56 hydrogen exist in your carotene, right? Or in your beta carotene. Now, there is 11 double bond, right? How do we confirm? And you know, that is by hydrogenation reaction or by addition reaction. So when your beta carotene react with 11 molecules of hydrogen, then they finally convert into perhydro beta carotene. Then they finally convert into perhydro beta carotene, C40H78, right? So 11 hydrogen molecule add 11 hydrogen molecule add beta carotene, right? So by this reaction we confirm about existence of 11 double bond in your beta carotene, right? So hydrogenation reaction clear us about 11 double bond exist in our beta carotene. Now after that, next point of discussion, this is related to the compound is either monocyclic, bicyclic, or tricyclic. So as I already told, in your compound, in your beta carotene, 2 cyclohexene. So it means your compound is bicyclic in their nature. It means your compound is bicyclic in their nature. How do we confirm that? It is on the basis of their general formula. You can see, right? After complete saturation or after hydrogenation of beta carotene, they absorb 11 hydrogen molecules and they finally convert into perhydro beta carotene, where their formula is C40H78, right? And it belongs to CnH2n minus 2. You know, CnH2n minus 2 means it is bicyclic compound, because we had already discussed if the formula is CnH2n minus 4, it means your compound is tricyclic in their nature, as we had already discussed about abitic structure, right? But when we talk about beta carotene, so they follow or they belong or they correspond CnH2n minus 2. It means your compound is bicyclic in their nature. Now after that, next point of discussion, this is related to conjugated double bond, right? There are 11 double bond, but the point is either they are conjugated double bond or simple double bond, right? So actually 5 conjugated double bond exist. 5 conjugated double bond exist in beta carotene. How do we confirm that? It's by addition reaction with malic anhydride, right? So when your beta carotene react with 5 molecules of malic anhydride, then they finally convert into a crystalline adduct, right? They finally convert into crystalline product, right? And they absorb they absorb 5 malic anhydride molecule. We had already discussed same type of reaction in abatic acid, right? So because in abatic acid, one conjugated double bond, so they absorb 1 mole of malic anhydride. But in case of beta carotene, it absorb 5 mole of malic anhydride. It means your beta carotene, right? It means in beta carotene, 5 conjugated double bond exist, right? So it is, and it is an important reaction which confirm about 5 conjugated double bond exist in your abatic acid. Now after that, next point of discussion, I already told cyclohexene. It means cyclohexane. It means cyclohexane exists in your compound, right? And 2 cyclohexane exist in your compound. How do we confirm that? It is by the oxidation of beta carotene. So when we do oxidize beta carotene with a strong oxidizing agent, that is potassium permanganate, then they convert into beta ion. 2 molecules of beta ion, right? Why they convert into beta ion? One beta ion have one cyclic compound, right? It is acyclic, one cycle. It means two cycle, right? It confirms the number of 2 cycle in your carotene, right? And other thing, it also give idea about site or methyl group, right? Substituted methyl group, right? So in this way, next one reaction. After that, when you oxidize beta carotene with ozone, then they convert into two molecules of gyronic acid. Right? So beta carotene, after oxidation in presence of ozone, convert into gyronic acid, right? And that gyronic acid on oxidation give 2,2-dimethyl glutaric acid. This reaction useful for confirm the presence of side methyl group exist in your compound, right? So we already know two methyl group exist at this position and one methyl group exists at this position, right? So gyronic acid, when your beta carotene oxidized by ozone, then they convert into this molecule, two molecule, right? Then they convert into these two molecules. So gyronic acid clear about this methyl group, right? Presence of one methyl group, right? And then after oxidation, they lose one acetic acid and they convert into 2,2-dimethyl glutaric acid. Right? After that, once again oxidize, they convert into 2,2-dimethyl succinic acid. And after that, their oxidation with a strong oxidizing agent, they lose one CH3COH acetic acid, and then they convert into dimethyl malonic acid. Right? So in this way, on the basis of final product, dimethyl malonic acid, you can say there are two side group or two methyl group. And on the basis of gyronic acid, you can say one methyl group exists at this position. So it is with both gyronic acid which formed after oxidation of your beta carotene with ozone, right? It should be clear. This reaction is very useful for confirm the presence of methyl group at beta carotene, right? So this should be clear, right? We had already discussed, I think, this reaction. Now after that, you can see, if we talk about simple structure of beta carotene, then you can see, right, one cyclohexene and two cyclohexene. How we can say there are two cyclohexane? It is on the basis of two molecule of gyronic acid formed from this reaction. So beta carotene on oxidation convert into two molecule of guronic acid. It confirm there are two cyclohexene. There are two cyclohexene, right? It is clear here, right? Second important thing, because they give beta ion, two molecules of beta ion, right? So it means it is a combination. It means your beta carotene is a combination of two ions, right? So you can see here, if you think about simple structure of your beta carotene, so it is like this, right? So this is your one molecule and this is your two molecule, ionic molecule, which are connected by C14s, which are connected by 14 carbons, right? So in this way you can see, in this way you can see, right? So this is basic structure of beta carotene. Now after that we come on next point. It is about number and position of side chain, right? So when we do destructive distillation, when we do destructive distillation of beta carotene, then they convert into this types of compound. Then they convert into this types of compound, right? So first compound like this, right? Second compound like this, and third compound like this, right? First compound like this, second compound like this, and third compound like this. And if you do their cyclization, then they finally convert into product like toluene. They finally convert into product like metaxylene, right? And this also convert into, you can see, if one group come at this position in second group, so 1,6-dimethyl naphthalene. If you combine these two carbon and these two carbon, so because one carbon, then two, then three, then four, then five, then six, it means they convert into 1,6 dimethyl naphthalene, because two benzene ring, no? So they will convert in, if it convert into toluene, if it convert into a metaxylene, and if then it convert into 1,6-dimethyl naphthalene, right? So on the basis of these three compound, one is toluene, second is metaxylene, and third is 1,6-dimethyl naphthalene, we can explain easily the structure of your beta carotene, right? So how these compound form? Either we talk about toluene, we talk about metaxylene, or we talk about 1,6-dimethyl naphthalene, right? So how do we confirm? 1, 2, and 3. How they form? They formed by cyclization of acyclic compound, right? So it means there are acyclic compound, right? There are methyl group at first position. There are methyl group at first and third position. There are methyl group at 1 and 6 position. And there are methyl group at 1 and 5th position, because 1,3 position, right here 1,3 position, here 1,5 position, and 1,6 position, right? So these are the position of methyl group confirmed by these compound formed after cyclization, राइट तो जब कंपाउंड का साइक्लाइजेशन होता है, पहले तो आपने डिस्ट्रक्टिव डिस्टिलेशन किया किसका, बीटा कैरोटीन का, और डिस्ट्रक्टिव डिस्टिलेशन करने के बाद जो कंपाउंड बने उन कंपाउंडों का, राइट, इफ यू डू साइक्लाइजेशन so then they convert into toluene, they convert it means some of the molecule of toluene, some of the molecule of metaxylene, and some of the molecule of 1,6 naphthalene formed from that reaction, which confirm position of methyl groups, right, exist in our compound or in beta carotene, right? And based on that, in order to explain the step A, B, and C, the following symmetric structure of beta carotene is proposed, right? So on the basis of these three structure, A, then B, then C, right? So on the basis of, because here 1,5 position, here 1,6 position, right, 1,3 position, finally we can conclude the structure of beta carotene or symmetric structure of beta carotene like this, right? Because if I talk about this, you can see here, right? So here, right, 1,5, you can see one methyl group at this position, second methyl group, then third, then fourth, then five, right? So methyl group at first and fifth position, then methyl group at first and sixth position, then methyl group at 1 and 5 position, and you can see 1, 2 and 3. It means methyl group at third position, right? So because methyl group at third position, methyl group at fifth position, methyl group at sixth position, this is region. Sometime the product is toluene 1,3 combination, sometime the product is metaxylene, and sometime the product is 1,6-dimethyl naphthalene, right? So these three products, one is toluene, right? One is toluene that is formed from this. This compound formed in toluene. Actually, this compound convert into toluene, right? Because 1 and 3rd position of methyl group, so they convert into toluene, right? 1,5 convert into metaxylene, right? And 1,6 convert into 1,6-dimethyl naphthalene, or 1,3 also convert into metaxylene, right? So metaxylene, 1,6-dimethyl naphthalene, and toluene confirm there are the position of methyl group at third, the position of methyl group at fifth, the position of methyl group at sixth. So in this way, right, you confirm this structure. Now after that, the compound is symmetric. The compound is symmetric. The conformation of symmetric structure of beta carotene. Now the point comes, conformation of symmetric structure of beta carotene. So beta carotene on oxidation, beta carotene symmetric. If we talk about symmetric structure, the structure of beta carotene is symmetric or not, right? So for that, this reaction is very useful, right? Beta carotene on oxidation with potassium dichromate, beta carotene on oxidation with potassium dichromate convert into dihydroxy beta carotene. That convert into dihydroxy beta carotene, right? Which on oxidation with lead tetraacetate, which is mild oxidizing agent. It means alcohol convert into aldehyde or ketone, not carboxylic acid, right? So here dihydroxy beta carotene, when oxidized with lead tetraacetate, they convert into semi beta carotenol. They convert into semi beta carotenol, right? So they convert into this types of compound. First dihydroxy and then carotenol, right? Semi beta carotenol. And once again, if you oxidize that by strong oxidizing agent like chromium trioxide, they convert into beta carotenol. Semi, because only one hexene, right, cyclohexene participate. So semi, and if both part oxidize, then this is called beta carotenol, right? So in this way we can say, your beta carotene, in this way you can say your beta carotene is a symmetric compound. Your beta carotene is a symmetric compound, right? So how do we confirm our beta carotene is a symmetric compound? So this is the point, right? So in this way we can clear about the structure. In this way we can clear about the structure of beta carotene.